This is seventh and last module of chapter 2. This module is devoted to bivariate interpolation. In previous module, we have discussed several methods for interpolation, and it is assumed that the problem contains only one independent variable and one dependent variable. But in practical situation, we have seen that the problem may contains two or more variables, independent variables, and one dependent variables. So, for this type of problem, we need a separate interpolation methods, and this kind of interpolation methods are called bivariate or multivariate interpolation methods. A lot of bivariate interpolation methods are available in literature. In this module, we have discussed 4 bivariate interpolation methods. Actually, two approaches are used in bivariate interpolation. One is called matching method and another is called approximate method. In matching method, for a given table of values of two independent and one dependent variables, a function or a polynomial is constructed for the dependent variable that satisfy exactly the functional values at all the given points. And in approximation method, a function or a polynomial is constructed that approximately fits the data. That means the fitted curve does not necessarily passes through the given points of the values. This approach is desirable when the data likely to have errors and require smooth functions. Again, the matching methods are of two types. One is called the local matching methods and other is called the global matching methods. Again, the local matching methods are of different kinds. One is triangular interpolation method, other is rectangular grid or bilinear interpolation methods, which are commonly used as a local matching methods. First, we discuss the triangular interpolation method. This is the very simple local matching interpolation method, and for this case we assume that a local interpolation surface of the following form, capital F of xy equal to a plus bx plus cy. The values of the constant a, b, c are evaluated based on the given data. These values are determined from the three corners of a triangle. That is why this method is known as the triangular method or triangular interpolation method. This procedure generates a space-wise linear surface which is global continuous. Let the function small f of xy, that means this function small f of xy is the given function, but its explicit form is not known, but the 3 points x1 y1, x2 y2 and x3 y3 are given or known. That means the vertices of a triangle are given. Let small f1 equal to f of x1 y1, f2 equal to small f of x2 y2 and f3 equal to small f of x3 y3. These are the given values. That means the values of f1, f2 and f3 are known. Let the interpolating polynomial be capital F of xy equal to a plus bx plus cy such that f of capital F of xi yi equal to small f of xi yi for all I equal to 1 to 3. That means the functional value is exactly matched with the interpolating value. So, using these values, that means using these 3 corner points x1 y1, we obtain small f1 equal to a plus bx1 plus cy1, f2 equal to a plus bx2 plus cy2, f3 equal to a plus bx3 plus cy3. Our problem is to find the values of a, b, c from these 3 equations. Now, solving these 3 equations, we obtain the value of a, b, c as this one. That means the value of a, b, c depends on the value of delta, where delta is equal to x2 minus x1 into y3 minus y1 minus x3 minus x1 into y2 minus y1. By substituting the values of a, b, c in equation 1, we get the required polynomial or required surface. But the function f of xy, the approximate function capital F of xy can be written in the following form: capital F of xy equal to capital A into f1 plus capital B into F2 plus capital C into F3. This is the rearranged form of the function f of x y, capital F of x y, where capital A is equal to x2 minus x into y3 minus y minus x3 minus x into y2 minus y whole divided by delta. Similarly, B and C are defined in equation 4 and 5. Note that in this expression, the values of A, B, C does not depends on the value of the function small f of x y, that means the value of f1, f2 and f3. Now, we observe the following important points. First one is, if the values of, that means the sum of the values of A, B, C equal to 1, then the denominator must not equal to 0. If delta equal to 0, that means the denominator is equal to 0, then the points xi, yi equal to 1 to 3 are collinear. This gives the condition for collinearity. Suppose xi, yi and f of xi, yi I equal to 1 to up to n are given. If we choose non-overlapping triangles which cover the entire region containing all these points, then a continuous polynomial can be constructed in this region, and this polynomial is the final surface for the bivariate interpolation formula. This method is illustrated by an example. Here we assume that f of 1 1 equal to 3, f of 3 1 equal to 8 and f 2 2 equal to 15. These are the given values. Now, our problem is to find the approximate value of f at 2, 1.5 using triangular interpolation method. So, for this case or for this problem, x1 equal to 1, y1 equal to 1, x2 equal to 3, y2 equal to 1, and from third value x3 equal to 2, y3 equal to 2. And the first value f1, the functional value f1 equal to 3, f2 equal to 8 and f3 equal to 15. These are the given values, and our problem is to find the approximate value of small f at x equal to 2 and y equal to 1.5. So, for this problem we have to determine the value of delta, and which is equal to x2 minus x1 into y3 minus y1 minus x3 minus x1 into y2 minus y1, and by substituting the values of x1, x3, x2, y1, y2, y3, the value of delta is equal to 2. Similarly, the value of A is equal to 0.25, value of B is equal to 0.25 and value of C is equal to 0.50. So, using these values, the approximate value of f at 2, 1.5, which is equal to approximately capital F of 2, 1.5, which is equal to A f1 plus B f2 plus C f3. Now, the value of A, B, C are 0.25, 0.25 and 0.50, and the value of f1, f2, f3 are 3, 8 and 15. Using this value, after simplification, we get the value of f at 2, 1.5 is approximately equal to 10.25. Now, we discuss another local matching interpolation method known as bilinear interpolation formula. In this method, 4 corner points of a rectangle are needed. Suppose the function small f of x y be known at the point x1, y1, x1 plus h, y1, x1, y1 plus k and x1 plus h, y1 plus k. These are the 4 corners of a rectangle. Based on this point, we construct a bilinear polynomial capital F of x y, which passes through these points and defined within the rectangle. So, for simplicity, we assume that f1, small f1 equal to f of x1 y1, f2 equal to f of x1 plus h, y1, f3 equal to f of x1, y1 plus k, and f4 equal to f of x1 plus h, y1 plus k. Let the polynomial capital F of x y be the following form. capital F of x y equal to a plus b into x minus x1 plus c into y minus y1 plus d into x minus x1 into y minus y1. Note that the polynomial 6 is a surface in 3-dimensional space. Now our problem is to find the value of a, b, c and d. This polynomial must persist through the given points. That means capital F of x1 y1 equal to small f1, capital F of x1 plus h comma y1 equal to small f2, capital F of x1 comma y1 plus k equal to f3, capital F of x1 plus h comma y1 plus k equal to f4. So, using these 4 corner points in equation 6, we obtain the following 4 equations: f1 equal to a, f2 equal to a plus bh, f3 equal to a plus ck and f4 equal to a plus bh plus kc plus hk into d. Now, we have to find the values of a, b, c from these 4 equations, and the solution of this equation is a equal to f1, b equal to f2 minus f1 by h, c equal to f3 minus f1 by k and d equal to f4 plus f1 minus f2 minus f3 whole divided by hk. Thus, the required bilinear polynomial is given by equation 6 and the values of the unknowns a, b, c and d are given by the equation 7. Now, this method is also illustrated by an example. Here we consider 4 corner points of a rectangle, that means 2, 2, 3, 2, 2, 3 and 3, 3 such that f22 equal to 4, f32 equal to 20, f23 equal to 15 and f33 equal to 25. These are the given values. We have to construct a bilinear polynomial capital F of x y based on this data, and we have to determine the approximate value of small f at x equal to 2.50 and y equal to 2.75. So, for this problem x1 equal to 2, y1 equal to 2, x1 plus h equal to 3, y1 equal to 2, x1 equal to 2 and y1 plus k equal to 3, x1 plus h equal to 3 and y1 plus k equal to 3. That means, it is easy to observe that h equal to 1 and k equal to 1. Also, small f1 equal to 4, small f2 equal to 20, small f3 equal to 15, small f4 equal to 25. These are the given values. So, using these values, we obtain the value of a equal to f1 equal to 4, the value of b equal to f2 minus f1 by h, which is equal to 16, c equal to f3 minus f1 by k, which is equal to 11, and d equal to f4 plus f1 minus f2 minus f3 whole divided by hk, and this is equal to minus 6. That means, we obtain all the values of the unknown a, b, c, d, and using this value, we get the bilinear polynomial as small f of x y is approximately equal to capital F of x y equal to a plus b into x minus x1 plus c into y minus y1 plus d into x minus x1 into y minus y1, and which is equal to 4 plus 16 x minus 2 plus 11 y minus 2 plus 6 into x minus 2 y minus 2. So, this is the final bilinear approximate polynomial for the given table of values. Also, f of small f of 2.50 comma 2.75 equal to 18 by substituting the values of x equal to 2.50 and y equal to 2.75 to the above expression, and this is the final approximate value of f at the given points 2.50 and 2.75. So, we have discussed 2 local matching method. One is called the triangular interpolation method, other is called the rectangular or bilinear interpolation method. Now, we shall discuss another bivariate interpolation method. One is called the Lagrange bivariate interpolation method and other is called Newton bivariate interpolation method. the Lagrange bivariate interpolation method is straightforward extension of Lagrange univariate interpolation method, but the Newton bivariate interpolation method is somewhat different. It is not exactly or not the extension of the Newton single valued interpolation formula. Now, we discuss Lagrange bivariate interpolation method. So, for this interpolation method, we consider m plus 1 into n plus 1 distinct points xi, yi, for which the value of the function f of xy are given. Let capital F of xy be the interpolating polynomial of the function small f of xy. The degree of capital F of xy is at most m in x and n in y, and which satisfy the condition capital F of xi yj equal to small f of xi yj, where I equal to 0, 1 up to m and j equal to 0, 1 up to n. So, this is the first criteria of the local matching formula of interpolating formula of any kind of interpolating formula. So, as in single variable case, the Lagrangian functions are defined as Lxi at x equal to Wx of x whole divided by x minus xi into Wx dash, that means the derivative of Wx at xi, which is defined for all I equal to 0, 1, 2 up to m. Similarly, Lyj of y equal to Wyy divided by y minus yj into Wy dash at yj, and this is true for all j equal to 0, 1, 2 up to n. That means the equation 9 and 10 gives the Lagrangian function for x alone and for y alone, where Wx of x equal to x minus x0 into x minus x1 up to x minus xm, and Wy of y equal to y minus y0, y minus y1 up to y minus yn. It is easy to observe that the functions Lxi of x is a polynomial in x of degree m, and Lyj of y is another polynomial of y of degree n. These functions also satisfies the following condition. These conditions are similar to the Lagrange interpolation polynomial in case of single variable, and Lxi at xk equal to 0 if xi and xk are different, and it is 1 if xi and xk are equal. Similarly, Lyj of yk equal to 0 if xy and yk are different, and equal to 1 if yi and yk are same. Using these notations, the Lagrange bivariate polynomial is given by capital F of xy equal to summation I equal to 0 to m into summation j equal to 0 to n Lxi x Lyj of y into f of xi yj. So, the equation 12 is the final Lagrange bivariate polynomial. Now, we consider an example to illustrate the Lagrange bivariate interpolation method. Let f00 equal to 1, f of 01 equal to 2, f of 10 equal to 3, f of 11 equal to 5, f20 equal to 5, f21 equal to 10 are known. Our problem is to construct a bivariate interpolating polynomial using Lagrange method and also calculate the value of f at x equal to 1.5 and y equal to 0.75. So, for this problem, m equal to 2, that means the number of arguments for x is 2, and n equal to 1, that means x0 equal to 0, x1 equal to 1, x2 equal to 2, that means the number of arguments of x is 3 not 2, and y0 equal to 0, y1 equal to 1. The Lagrangian functions are Lx0 of x equal to x minus x1 into x minus x2 whole divided by x0 minus x1 into x0 minus x2 after substituting the values of x0, x1 and x2, this expression is reduces to half into x square minus 3x plus 2. Similarly, Lx1 of x is equal to minus x square minus 2x, Lx2x equal to half of x square minus x, and similarly Ly0 of y equal to y minus y1 whole divided by y0 minus y1 equal to 1 minus y, and lastly Ly1 of y equal to y minus y0 y1 and lastly ওখান থেকে আবার বলুন
সাইলেন্স এন্ড লাস্টলি থেকে আবার যাচ্ছে রোল
and lastly Ly1 of y equal to y minus y0 whole divided by y1 minus y0, and this is equal to y. So using this value, the Lagrange interpolating polynomial is f of xy equal to summation I equal to 0 to 2, summation j equal to 0 to 1. In this case, the value of m is 2 and the value of n is 1. So the range of I and j are 0 to 2 and 0 to 1 of Lxi of x into Lyj of y into f of xi yj. Now by expanding the values of j and I, we get the polynomial capital f of xy equal to Lx0x second bracket start Ly0y into f of x0y0 plus Ly1 of y into f of x0 comma y1 second bracket close and so on. After using the values of Lx0, Lx1, Lx2, Ly0, Ly1 and all other values of f, we get the value of capital F of xy equal to half of x square minus 3x plus 2 into 1 minus y into 1 plus y into 2 minus x square minus 2x whole into 1 minus y into 3 plus y into 5. After simplification, this expression reduces to x square y plus 2x plus 1. Hence, the value of f at x equal to 1.5 and y equal to 0.75 is approximately equal to capital F of 1.5 comma 0.75, and using the value of x 1.5 and the value of y equal to 0.75 to the above expression, we get the approximate value as 6.4375. So this is the approximate value of small f when x equal to 1.5 and y equal to 0.75 obtained from the above expression. Now we consider another bivariate interpolation formula known as Newton's bivariate interpolation formula, and for this case we consider a set of bivariate points, that means xi yj at m plus 1 into n plus 1 distinct positions, and also we assume that xi equal to x0 plus ih and yj equal to y0 plus jk. This condition actually indicates that the arguments x and y are of equal spacing. Also we assume that x equal to x0 plus sh and y equal to y0 plus tk. That means s and t are the two new variables. So we define some first order and higher order differences with respect to x and y. Now delta suffix x indicates the forward difference operator for the variable x. So delta x of f of xy is equal to f of x plus h comma y minus f of x comma y. Note that the value of y remains unchanged, only the value of x are changed. So using the shift operator, the first term is equal to e suffix x of f of xy minus f of xy which is equal to Ex minus 1 of f of x y. Similarly, delta y of f of x y means the forward difference on the variable y, which is equal to E y minus 1 of f of x y, and del xx f of x y, del xx means the forward difference operator is applied on the argument x for 2 times, and after simplification it can be shown that the delta xx indicates this is the forward difference operator applied on the first argument x, and after simplification it can be shown that this operator is equivalent to Ex2 minus 2Ex plus 1 of f of xy, and it is written as Ex minus 1 power 2 of f of xy. Similarly, delta yy f of xy is equal to Ey2 minus 1 power 2 of f of xy. And using the same concept, we can show that delta xy f of xy is equal to Ex minus 1 of Ey minus 1 of f of xy. So, these are the forward difference operator for the variable x and y. Now, let us consider the function f of xy as f of xy equal to f of x0 plus sh. We have written that x equal to x0 plus sh and y equal to y0 plus tk, that therefore, f of xy is equal to f of x0 plus sh comma y0 plus tk, and this is equal to Ex power s of Ey power t of f of x0 y0. Exs and Eyt are the shift operator with respect to x and with respect to y respectively. Again, we know that Ex is equivalent to 1 plus delta x. So, this expression is reduces to 1 plus delta x power s of 1 plus delta y power t of f of x0 y0. By expanding the terms 1 plus delta x power s, we get 1 plus s into delta x plus s into s minus 1 by factorial 2 into delta xx plus dot dot dot. Similarly, 1 plus delta y power t is equivalent to 1 plus t into delta y plus t into t minus 1 by factorial 2 into delta yy plus dot 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 of f of x0 y0. So, after simplification, the entire expression is transferred to 1 plus s into delta x plus t into delta y, this is the first difference terms, plus s into s minus 1 by factorial 2 into delta xx plus t into t minus 1 by factorial 2 into delta yy plus st into delta xy and so on. Note that there are 3 terms present which are of second order differences. So, whole this expression is applied on the function f of x0 y0. So, this is the approximate expression for the function f of xy in terms of the variable s and t and the first order, second order differences of x and y. For simplification of the above expression, we can use another kind of transformation. That means, if we substitute s equal to x minus x0 by h and t equal to y minus y0 by k, this is also the values of s and t we have substituted in previous slide. Then s minus 1 equal to x minus x1 by h and t minus 1 becomes y minus y1 by k. So, using this notation, the above expression becomes capital F of x y equal to f of x0 y0 plus square bracket start x minus x0 by h into delta x plus y minus y0 by k into delta y. Whole expression is applied on the function f of x0 y0 plus 1 by factorial into some second order differences. So, the expression 13 is the Newton's bivariate interpolation formula. But using suitable variable, this expression can also be simplified in a simple form or simple expression, which is discussed in next slide. To simplify this formula, we use two unitless quantities u and v, which are defined by x equal to x0 plus uh and y equal to y0 plus vk. Therefore, x minus x s equal to u minus s whole into h and y minus yt equal to v minus t into k. Using this notation, the equation 13 becomes capital F of xy equal to f of x0 y0 plus u into delta x plus v into delta y of f of x0 y0 plus 1 by factorial 2 u into u minus 1 delta xx plus 2 uv into delta xy plus v into v minus 1 delta yy. Whole expression is applied on the function f of x0 y0 and so on. So, equation 14 is the final expression for the Newton's bivariate interpolation formula. Now, we consider one example to illustrate this formula. So, for a function f of xy, the values of f of 0 0 equal to 1, value of 0 1 equal to 2, value of 0 2 equal to 3, value of 1 0 equal to 4, value of f11 equal to 0, f12 equal to 4, f20 equal to 2, f21 equal to minus 2, f22 equal to 3 are given. So, for these values, our problem is to construct the Newton's bivariate interpolating polynomial, and from this interpolating polynomial calculate the approximate values of f at x equal to 1.25 and y equal to 0.75 and the value of f at x equal to 1 and y equal to 1.5. So, for this problem, delta x of f of x0 y0 equal to f of x1 y0 minus f of x0 y0 equal to 4 minus of minus 1, that means the value of f of x1 y0 equal to 4 and value of f of x0 y0 equal to minus 1. Thus, the finally delta x f of x0 y0 equal to 5. Similarly, delta y f of x0 y0 equal to 3 and delta xx f of x0 y0 which is equal to f of x2 y0 minus 2 f of x1 y0 plus f of x0 y0 which is equal to 2 minus 2 into 4 plus of minus 1 and this is equal to minus 7. Similarly, delta yy of f of x0 y0 equal to minus 2 and finally, delta xy of f of x0 y0 equal to minus 7. So, for this case h and k are equal to 1, u equal to x minus x0 by h, this is equal to x because x0 is 0 and h equal to 1. Similarly, v equal to y because v equal to y minus y0 by k gives y since y0 equal to 0 and k equal to 1. Thus, the approximate polynomial capital F of xy for the function small f of xy is capital F of xy equal to 1, this is the value of f of x0 y0 plus x into 5 plus y into 3 plus 1 by factorial 2 into x minus 1 into minus 7 plus 2 xy into minus 7, this is the value of delta xy plus y into y minus 1 into minus 2, this is the minus 2 is the value of delta yy. After simplification, this expression reduces to half into 2 plus 17x plus 8y minus 7x square minus 14xy minus 2y square. Now, the approximate values of f at 1.25 comma 0.75 is approximately equal to capital F of 1.25 comma 0.75 which is equal to 2.03125 and the approximate value of f of 1.0 comma 1.5 is equal to capital F of 1.0 comma 1.5 which is equal to minus 0.75. So, these values are obtained by substituting the values of x and y to the above expression. And diagrammatically, the polynomial capital F of xy is shown in this slide. So, this is a surface, obviously a surface in 3 dimension, and this is nothing but the interpolated bivariate polynomial obtained from the data presented in previous slide. In this module, we have discussed 4 bivariate interpolation formulas, and in chapter 2 we have discussed several interpolation formula such as a Lagrange interpolation method, Newton divided difference interpolation methods, and these interpolation methods are applicable for all kinds of data, that means for equal as well as unequal space arguments. Also, we have discussed about Newton's forward and backward difference interpolation formula. We have discussed Gauss central difference formula along with Stirling and Bessel interpolation formula. All these formulas are applicable for only equal space arguments. Again, we have discussed Atkin iterative interpolation formula. We have discussed Hermite interpolation formula. In Hermite interpolation formula, we have considered the first derivative of the function. Also, we have discussed the spline interpolation formula, particularly cubic spline interpolation formula, and all these interpolation formula are used in many practical applications, particularly computer graphics, image processing, and many other things. But even then, lot of interpolating methods are not considered in chapter 2. So, the interested readers can consult with the books and website which are mentioned in the references.